Good morning, boys and girls, and welcome back to our discussion on series. Today we're going to look at some real interesting stuff and talk about the difference between absolute and conditional convergence. But let's start us off with an interesting series and discuss it. Let's look at the series of n to 1 equals 1 to infinity of sine n over n squared. If I wrote out the terms, it would look like this. Sine of 1 over 1 plus sine of 2 over 4 plus sine of 3 over 9. Sine of 4 over 4, sine of 5 over... That doesn't look that interesting, really. But now if I go look at the decimal equivalents of these, when I round to two decimal places, we get 0.84 plus 0.22 plus 0.015. So things are kind of looking good, everything's positive. But then all of a sudden we get a negative term, minus 0.04, minus 0.03. The next one's going to be a minus, and this is switch back to pluses. Because that sign bounces back and forth between positive and negative values, we're going to have some positive terms, we're going to have some negative terms. However, this is not an alternating sequence. It doesn't go positive, negative, so I can't use my alternating sequence stuff. And they're not all positive terms, so I can't use any of our other tests that lead up to this. So this is what we're going to talk about today, is how do we deal with a situation like this? Okay, so when you come across a series like this that have both positive and negative terms, but they're not alternating, they're just some positive, some negative, what we want to do is we're going to look at the absolute value of the series. That way, we're going to just make them all positive, and then we can use all of our rules. So I'm going to look at n equals 1 to infinity of the absolute value of sine n over n squared. And this would make all my terms positive, so now I can use my other tests. In this case here, we know that sine of n has to be less than or equal to 1 for all values of n, right? And then by direct comparison then, I know that, or at least, I know that sine n over n squared is going to have to be less than or equal to 1 over n squared, okay, for all n's. Greater than or equal to 1. So if that's the case, if this is smaller than 1 over n squared, well, then by direct comparison, I know that it's going to have to converge. And so since the absolute value of sine n over n squared converges by direct comparison with 1 over n squared, I can now say that our original series is also going to converge. And we're going to talk about why I can say that here in a second, but if the absolute value of the series converges, then the series also converges. All right? We call that absolute convergence. Okay, so here is the definition of absolute convergence, what absolute convergence is, and the difference between it and conditional convergence. What absolute convergence says is that if the sum of the absolute value of some sequence, of some series, if that converges, then that plane series is also going to have to converge. Okay? That's absolute convergence. If both the series and its absolute value, if they both converge, then it converges absolutely. Okay? And so again, we can use this like we did in that previous example. I can use this sometimes to prove that something that's not all positive or all negative terms. If I look at the absolute value of that series, if that converges, then I know the regular series is also going to have to converge because they will have to converge absolutely. Conditional convergence is a little bit different. You get conditional convergence if the series converges, but when you look at the absolute value of the series, that diverges. Right? A good example of this is our alternating harmonic series. Alternating harmonic converges, but the harmonic series diverges. So the alternating harmonic series converges conditionally. Right? It has a conditional convergence. All right, so let's use this idea here of absolutely and conditionally convergent. And let's look at a few series, and we want to first see if they are convergent or divergent. If they are convergent, then we're going to want to classify them as absolutely or conditionally convergent. All right? So, first one here we have negative 1 to the n times n factorial over 2 to the n. And I want to see, hey, is this going to be convergent or divergent? And then if it is it absolute or conditional? All right. So, because I want you guys to think about this, how would you attack it? Hopefully you're thinking the very first thing I'm going to do is I'm going to run it through our nth term test for convergence, right? That should be the first way we approach any series, is let's just make sure that passes that test first. When I do this test, I really just need to look at the n factorial over 2 to the n part. Again, that negative 1 to the n is just going to be the alternating, right? That's just going to change our sign. So I care about the terms. I want to, are my terms going to go to 0 or not? And in this case here, we have talked about how factorials are going to go faster than exponentials. So the top's going to go faster than the bottom. So no, this was going to go to infinity as I go. So because that goes to infinity, this fails the nth term test for convergence, and therefore this is going to diverge, and I don't have to do anything else. That's why we always want to do this test first, right? All right, so if we look at this one now, again, we have another alternating series I can see because we have the negative 1 to the n. If I run this through the nth term test, it is going to go to 0. Again, we can drop the negative 1 to the n part because that's just the alternating, and that's going to go to 0, so that is good. So that, well, that's the first part of my nth term test, but that's also, again, because it's an alternating series, the first step into proving that an alternating series is going to converge, that has to go to 0. So we've passed like step 1. Now I need, again, for alternating series, I need to show that it is getting smaller each term. So I'm going to go and look at the actual terms. And so if we start plugging in our n equals 1, 2, 3, I get negative 1 over root 1 plus 1 over root 2 minus 1 over root 3 plus 1 over root 4. So yes, my terms are getting smaller, right? They are getting smaller. So because the limit as n goes to infinity equals 0, and the terms are getting smaller or non-increasing, then this converges by the alternating series test. All right, so now that we know this now that we know this converges by the alternating series test, let's go and answer the question, does it converge conditionally, or does it converge absolutely? So to see if that's going to happen, we want to, again, look at the absolute value of this. I'm going to look at the series from n equals 1 to infinity of the absolute value of negative 1 to the n over root n. And so if I look at this series, we're really going to look at, that gets rid of that negative 1 to the n part, right? Because that's always going to be positive. And so I'm really going to look at this series n equals 1 to infinity of 1 over the square root of n. Okay? Or this would be 1 over n to the 1/2. Now, I know that because of p series, with my p less than 1, I know that this is going to diverge. And now because the original series converged and the absolute value diverged because of the p series with a p less than 1, I know that this is only going to converge conditionally. This is conditionally convergent. So that's what we mean to be conditionally converges. If the regular one does converge, but the absolute value does not. All right, let's do another one. Okay, so here's another funny, weird one. I guess it's really number 3, huh? Number 3. Negative 1 to the n times n plus 1 all over 2 divided by 3 to the n. Again, first thing I'm going to think or put this through the nth term test. But as n goes to infinity, this is just still going to be negative 1 to some power, so it's going to bounce back and forth between positive and negative. So the bottom is going to go to infinity, so this will go to 0. So it passes the nth term test for convergence, so this could converge. So now let's go and look at the terms as we see some potential alternating series stuff here. Now if I plug 1 into here, I'm going to get 1 times 1 plus 1, so 2. So 1 times 2 is 2, divided by 2 is 1. Negative 1 to the first is negative, so I get negative 1/3. Now if I plug in 2, I'm going to get 2 plus 1 is 3, times 2 is 6, divided by 2 is 3, so negative 1 to the third is still negative, and then over 3 squared is 9. And if I plug in 3, then I'm going to get a positive, and if I plug in 4, I'm going to get a positive, and I'll let you kind of look through that math. But basically, we're going to get like negative, negative, positive, positive, negative, negative, positive, positive. So this is not an alternating series exactly, because alternating has got to go plus, minus, right? So it's not alternating. We have some positive, some negative ones. And so again, when we have a series like this, what we want to do is we want to look at the absolute value of this to see if it's going to converge or not. Okay, that's the trick we use here. And if I look at the absolute value of this series, that gets rid of all this nonsense on top, and that's always going to be a positive 1. So this basically becomes a series of 1 over 3 to the n. And now again, hopefully remember when we see one like this, again, I know in the beginning I used to confuse it with p-series. It is not a p-series though. This really can be written as 1 over 3 to the n, because I can raise 1 to any power that I want to, and it's still going to be 1. So this is really a geometric series. And it's a geometric series with an r of less than 1, so yes, this is going to converge. And because the absolute value converges, then the whole thing will converge absolutely. So if the regular series converges and the absolute value series converges, then it converges absolutely. Or just if the absolute value converges, then we know they both are going to converge absolutely. Okay, so in this case, both those series converge, and they converge absolutely. All right, one more. All right, we got the series 1 to infinity of negative 1 to the n over ln of n plus 1. This is an alternating series. So let's run it through the nth term test for divergence first. If we look at this limit, yes, as we go to infinity, ln of infinity is going to go to infinity, so this is going to go to 0. So there's my first step of showing that this is going to converge. Again, next we're going to look at our terms to see if they get smaller or not. So let's write them out. All right, we get 1 over ln2 plus 1 over ln3 minus 1 over ln4 plus 1 over ln5. And so yes, those are slowly getting bigger. Therefore, my numbers are getting smaller. And so yes, this converges by the alternating series test. Okay, and because this converges by the alternating series test, let's look at the absolute value to see if it converges conditionally or absolutely. All right, so now we get 1 over ln of n plus 1. We want to look at this series to see if that is going to converge. We already know that it's going to pass the nth term test, so it's got the possibility to. Let's see. We could do the integral test, probably, but that's a lot of work, and you got an ln, so it probably means a little ultraviolet. So I'd probably try to stay away from that if I could. I think I want to compare this with something, and either use direct comparison or a limit comparison test on this. And I think in this case, let's try to directly compare. It's usually easier. I'm going to try to directly compare it to 1 over n. All right, so if I look at these terms, 1 over n is 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5. And I know that this is going to diverge because that is the harmonic series. 1 over our function, I get 1 over ln2 plus 1 over ln3 plus 1 over ln4. And if you look at those decimal equivalents here, this is like 1 over 0.69, 1 over 1.09, 1 over 1.3. So I'm dividing 1 by a smaller number than I am here, which would make my function bigger. So I do know that this is larger than that function right there. So again, with direct comparison, if the smaller function diverges, it is going to force that larger function to also diverge. So both these functions diverge. So 1 over ln of n plus 1 diverges by direct comparison with 1 over n. And all this work would be my justification that I just showed there. So because the original function converged by the alternating series test, and the absolute value diverged by direct comparison with 1 over n, then I know that this converges conditionally. So it is conditionally convergent. Yay! Alright, one last thing to talk about here real quick, and that's the rearrangement of a series. If you would rearrange the terms in a series, is it going to give you the same sum? Right? Well, it turns out for an absolutely convergent series, that is true. If a series is absolutely convergent, then every rearrangement, doesn't matter what order I put those numbers in, they will have the same sum. However, that is not true for a conditionally convergent series. Technically, the terms of a conditionally convergent series, infinite series, can be rearranged, and you can have them form any sum you want them to form. I'm going to, again, attach a little video at the end of this that you can look at from one of my favorite guys that I learned a lot of this calculus stuff from when I was first trying to, teach it to myself. So it might be good to hear it from him. And it's just a quick little, he plays around with the alternating harmonic series and gives you a kind of a quick little example of how things can be arranged. So watch the video. It's really kind of interesting how we can rearrange series, and it's not going to give us the same thing that we think it should. So check out that video, and there's a bunch on rearranging the alternating harmonic. If you got questions, come see me. Otherwise, see you later, boys and girls. Have a great day.